Good afternoon, everybody. Happy Friday, almost at the weekend here. So we've been moving through all of these different cycles in thermodynamics, and now we're down to our last new cycle, although I guess technically we'll talk about two different cycles: vapor compression refrigeration and vapor compression heat pumps. Now, it's two cycles, but ultimately it's almost the exact same process. There's only a slight difference in what we're calling the energy benefit of the cycle when we're defining the coefficient of performance. So in today's lecture, we're going to have an introduction to vapor compression and refrigeration, or to vapor compression refrigeration and heat pumps. And we'll be asking the question, do you want to build a snowman? So when we started to talk about thermodynamics, right? So we're getting close to the final, so maybe it's good to be a little bit retrospective, right? The first third of the class was looking at closed systems, right? And that helped us ultimately once we got to internal combustion engines. But then the second third of the class was how do we sort of model and analyze open systems? So we realized we needed to know something about conservation of mass and about conservation of energy, or the first law, for these open systems. Now, hopefully, at this point in the class, you're very familiar with how we go through an analysis for an open system or for a closed system. After we did the first law, we kind of learned that you can't always get what you want, right? So the universe, through the second law, is kind of showing us that every process has a natural direction. So just because the energy balances and we conserve mass doesn't necessarily mean that a process is possible. So we have to look at a second law analysis of open or closed systems as well. And first, we started to talk about, sort of this conceptual understanding of the second law. And we talked about Kelvin and Planck, and they told us that you can make an engine or a machine that takes heat in from some hot reservoir and produces work, but you can't do that unless that engine is allowed to cool, rejecting heat to some cold reservoir. So that's what Kelvin and Planck told us about the second law, and that was really nice at the time because people were thinking about steam engines. Right? We've talked about how in mechanical engineering, a lot of times if you give us heat, what we'll want to do is boil water, because when we boil water, we know that steam expands, and if it expands through something like a turbine, we can turn that physical process into mechanical work. So like I said, so they were using this to make things like locomotives, right? And I really like this picture just because I think it looks cool. Now, there's another important problem that deals with work and heat transfer. And that problem is, how do we keep food cold, right? Or at least that's kind of the answer that we've landed on in 2020, that we've been using for a pretty significant amount of time, definitely for generations, right? But earlier, people would preserve meat by salting it, or maybe they would smoke that meat. Or maybe your parents or your grandparents, or even maybe you live in a place that has a cold cellar, right? So my grandparents in their basement had a cold cellar where they would keep sort of, canned materials, right? So they had this room that was naturally cold because it was below ground. Now, when people were thinking about the second law, right, there's one way to think about the second law, like Kelvin and Planck did, and they said, okay, let's turn heat into work, right? Now, this is probably not actually how this happened, but it's at least kind of how I'm imagining it to have happened, right, is that somebody like Clausius came around, and he looked at these cold rooms, and he was like, well, can we make a machine that would keep a space cold? Right? Ideally, something as big as a room, but what if even if it was just a small area like a refrigerator, right? So can we make a machine that keeps a space cold? Because if we could, then we could put food in there and keep it cold, right? So Clausius's statement of the second law, and again, I said this when we first introduced these, I'm not a huge fan of the text of these statements of the second law. I prefer kind of the picture, right? But what Clausius' statement of the second law says, it's not possible to construct a device that operates on a cycle whose sole effect is the transfer of heat from a cooler body to a hotter body, right? Like I said, my old heat transfer professor said this was kind of like the 0th law of thermodynamics, is that heat always moves from hot places to cold places. So Clausius comes around and he said, well, maybe we can make a machine and we split it into sort of two halves, and this cold half of the machine is colder than our cold place, right? So if we're thinking about a refrigerator, then there's half of our machine is colder than the temperature we want to keep the air in the refrigerator. But the consequence of that, Clausius told us, is that, you have this other side that's hotter than the hot space, right? So maybe that's the air in behind your fridge, right? And Clausius told us that you can't do this and produce work or power at the same time. You can't even do this with no net power. In order to make a machine like this, you got to plug it into the wall, right? So your fridge consumes power when it operates. This is also true if you have an air conditioner. It's also true if you heat your house in the winter using a heat pump. So Clausius found out, and I mean lots of other people, right? If we can put mechanical work into this machine, then we can set it up so there's a cold part that's colder than our cold space and a hot part that's hotter than our hot space. So we can sort of, if we zoom out far enough, this makes it look like we're tricking the universe into transferring heat from a cold place to a hot place, right? So it's a bit of a magic trick, but in order to perform this trick, we need to put work into the system. And that's kind of this Clausius statement of the second law. And this is going to be really important for us in the next 2 lectures, because we're going to start to look at how refrigeration and heat pump cycles work. So this is a sketch from the textbook of a vapor compression refrigeration cycle. So if you have a refrigerator, this is probably the kind of cycle that your refrigerator runs on. I mentioned, I think before, that we just had our air conditioner fail, even though it was brand new, right? But it had sprung a leak. It turned out it was in the evaporator coils where it failed. So, I mean, the people who installed this one comes from the factory, right? One of the brazes was bad. So it was leaking refrigerant. I think the new refrigerant is called Preon. And it was basically leaking into my basement. So hopefully there's no long-term health effects from that, right? But this is a sketch of what this looks like, right? So I have coils inside my HVAC system here, right? This is the evaporator, and it's taking heat in from the air that blows over those coils. Now, outside of my house, I have a condenser and I have a compressor. But then there's this other part of the system, right, that we call an expansion valve. Now, you might look at this and say, this looks a little bit like a Rankine cycle, but it's all kind of backwards. And that's really what this vapor compression refrigeration cycles are like. They're like Rankine cycles, but they run in reverse, right? So a compressor is kind of like a pump. We don't have a turbine in this cycle. So this is, I guess, maybe if you didn't think hey, this looks like a Rankine cycle backwards, it might be because we have this expansion valve instead of a turbine. And they're a little bit similar. So the way that they're similar is that there is a pressure drop across this expansion valve, right? But an expansion valve, maybe it's just a really thin piece of tubing that your refrigerant flows through, so you get a pressure drop, right? There's different ways to construct these, but that's at least one way, right? So what we're getting here is a pressure drop, just like we get a pressure drop across a turbine. But there's no kind of blades inside this expansion valve. So we'll see how we treat this, but we'll see that it's treated a little bit differently than a turbine is. And then we have 2 different heat exchangers, one that's accepting heat, although this is weird because here we're taking heat in from the cold side, and one that's rejecting heat, and here we're rejecting heat onto the hot side. And the way that we do this is we have a refrigerant that's running through here. So this refrigerant, in our evaporator, it's boiling. So when we get this down to a liquid, its temperature, its evaporation temperature at whatever pressure is here, is going to be lower than the temperature we're keeping, the ambient temperature inside of our house, if we're talking about a residential air conditioner, or it's the air that's inside of our fridge, if we're talking about a refrigerator. So when we're talking about a refrigeration cycle versus a heat pump, these are almost the same thing. Remember, we talked about this a little bit before when we were talking about the second law. The difference between a refrigerator and a heat pump is the energy benefit. It's kind of like if you were drawing a little stick figure that's kind of, being placed where the energy benefit is. So inside a refrigerator, what we're trying to do is cool down the cold space. In a heat pump, we're trying to heat up the hot space. So the energy benefit for a refrigeration cycle is this heat transfer that comes in on the cold side. And we'll see that the energy benefit in a heat pump is the heat that goes into the hot side. So this is called a vapor compression refrigeration cycle, right? So when we compress a vapor, well, maybe we're doing that so that we can get to a liquid, right? So these vapor compression refrigeration and heat pump cycles, the reason that when we think about the working fluid here, it's not water. It's going to be some kind of refrigerant, right? So maybe it was Freon in the past, right? Maybe then it was 134A, and now it's Preon, right? So it's nice for us to be friends with chemical engineers because they're always making new chemicals. So things like new refrigerants that can be, still have good performance, but more environmentally friendly. But what's happening in thermodynamically as we run through this cycle is we're moving back and forth across the vapor dome, just like we did in a Rankine cycle, right? And you know this maybe because of the names of our heat exchangers. So one is called a condenser. What happens in a condenser? Well, the fluid condenses, right? Another is called an evaporator. So what happens in the evaporator? Fluid evaporates, right? So if we wanted to draw the whole cycle inside the vapor dome, which is maybe not the most practical thing, but it means we have one hot temperature and one cold temperature. Then as we went across this condenser, maybe we would start out here as a saturated vapor, and we would condense ourselves all the way down to a saturated liquid. So that's this process here going through this condenser from state 2 to state 3. If we had an ideal or an isentropic compressor, again, you'd probably not want to do this. You don't necessarily want to be compressing something that's a two-phase mixture, right? But if we did, then here it would be under the vapor dome, vertically below state 2, if this compressor was ideal or isentropic. Now, it's a little tricky here, right? Because we have this expansion valve. Now, the expansion valve is not going to be isentropic. So I have deliberately drawn this line as not vertical. In real life, it could be more vertical than what I'm drawing, but I want to make it clear that this is not an isentropic process. Delta S across the valve is not 0. We'll talk about how we'll model the valve, but for now, I want you to know that it looks like something that's not isentropic. Now here, if I was going through my cycle, right, so now I'm started, I compressed, I condensed, I went through this valve to drop my pressure, and now I want to evaporate my fluid, right? So I've got this cold, mostly liquid, or at least more liquid than over here. I'm adding heat from my hot side, and I move from state 4 to state 1, and now I've got something that looks like a cycle, right? I can start at any of these states, but state 1 is kind of makes sense, right? And we keep moving around and around as we go through this cycle. As I go through my compressor, I'm adding work, right? This is why you got to plug your fridge or your air conditioner into some kind of an electrical power source. We're rejecting heat through the condenser. Now, what's going to happen in the valve? I know that this is going to be adiabatic, and I've been saying that it's a little bit like a turbine, so at least here, I'm going to draw this as the valve getting power out of our cycle, right? So if I'm canceling out Q dot, then maybe I have some power term or some work term that's associated with this valve. So we'll leave it like that for now. And then in the evaporator, This is in the refrigeration cycle. This is the energy benefit. The whole reason that we're doing this is to remove heat from the hot place, and that happens in the evaporator, which is on the cold side of the cycle. It's a little bit counterintuitive, but remember, this whole cycle is kind of playing a trick on the universe to make it so that we can remove heat from the cold place. If we're talking about a refrigeration cycle, right? Really, any of our cycles, if we think about how we're characterizing them, remember, this is our first of our big questions when we think about cycles. What's the energy benefit divided by what's the energy cost? For the refrigeration cycle, the energy benefit is that we're removing heat from the cold side. So the energy benefit is going to be this Q dot term from the evaporator. The energy cost is that we need to be able to add power into the system, right? So I got to plug my fridge in. So how much, energy is it going to consume when I'm running this cycle? So we're talking about a coefficient of performance. We use Greek letters for coefficients of performance. So the way that I remember that the refrigeration cycle gets beta is that beta looks kind of like an R, at least if I squint a little bit. So a refrigeration cycle gets beta. If you don't want to remember that, you can change beta to just COP, which stands for coefficient of performance. So how are we going to find the coefficient of performance? Right? You guessed it, right? This is thermodynamics class. So what we're going to do is we're going to use the first law of thermodynamics, right? These are open systems. So just like a Rankine cycle, just like a Brayton cycle, just like a turbojet, all of these processes are happening in a different component. So we'll have to look at each one of the components and we'll make some assumptions. In this class, we're always going to say that things happen at steady state. We're almost always going to say that things are one inlet and one outlet. The time where that's not true was a Rankine regeneration cycle, right? Or I guess if you have some heat exchangers, then you know what's going on the hot side and the cold side. But we'll often say one inlet and one outlet. Here, it's not like our turbojet problem. We're going to neglect kinetic energy changes. We're going to neglect potential energy changes. We'll go through these different components. We'll assume usually that they're adiabatic or that they're passive. Throughout the whole cycle, we'll say that there's no friction losses and that there's no heat losses in the lines that are connecting our different components. So when we do this, we're going to get expressions that hopefully we're getting used to. If I'm trying to find a heat transfer term, it's going to be m dot times h out minus h in. Right? That's true for the evaporator and for the condenser. Remember, all of these components are at steady state in one inlet and one outlet. So the mass flow rate, even though I have different subscripts here, they're all the same mass flow rate. If I'm trying to find power through some kind of adiabatic process, then it's going to be m dot, in this case of the compressor, times h in minus h out, right? Hi-ho. So these are the expressions that I'm going to expect. Right? But again, we sort of have this valve. So to get here for the valve, I assumed it was adiabatic, right? So I can take this valve and I can insulate it, right? But, here it's looking like a turbine, like it's going to produce power for us. But remember, I've also said that, these processes where we're getting power, at least in open system processes, they're going to have fan blades in them. Right? So maybe it's a compressor and we're the ones spinning the shaft. So those fan blades are compressing our fluid, right? Or maybe it's like a turbine and a gas is expanding over those fan blades, which is causing that shaft to spin, right? But the valve doesn't have any fan blades in it, right? So we're going to make another assumption about the valve. So we know there's a pressure drop across the valve. So it could, at least theoretically, be possible to put some kind of turbine in there and get some power, right? But we're going to make the assumption, because there's no kind of fan blades in here, that we're not getting any power. So for these valves, even though they have a pressure drop, we'll make the assumption that they're isenthalpic. Now, remember, isenthalpic means delta H is equal to 0, right? It's a little bit like, remember, isentropic meant delta S was 0, right? So isenthalpic means the enthalpy doesn't change, right? So here, for the valve, H3 is equal to H4. So delta H across the valve is 0, which means that there's no power generated in the valve. this also means that the net power is only determined by the compressor. And since a compressor is like a pump and we're putting work into the system, that means that our net power is negative, right? Because this is something that's consuming power, and that's why we got to plug it into the wall, right? If we're talking about a refrigeration cycle, then it's the evaporator that we're interested in, which is Q dot on the cold side, because we're adding heat. We're adding heat to the working fluid by removing heat from our reservoir, right? So for these refrigeration cycles, we've got our coefficient of performance, which is beta, right? So again, if you don't want to remember which Greek symbol, just write coefficient of performance. Refrigerator maybe up here in the subscript, or maybe or up here in the superscript, maybe down here in the subscript, right? If we're trying to find this in the actual case, the real case, you'd have the desired energy effect divided by the cost, right? Now here, we're going to say that this is an absolute value, right? Even though, so Q dot in, right? Heat is coming into our evaporator, so this is a positive number, but work is going into our system, so this is a negative number. So maybe you get a coefficient of performance, something like, I don't know, 10 or 12 or something. If you're thumbing through the brochure of different refrigerators, it's not going to say that the coefficient of performance is negative 12. Because if you're the salesperson there, you don't want to be telling people how great it is, because it's got a bigger negative number for the coefficient of performance. So instead here, we take absolute values of both of these terms, right? So for this refrigeration cycle, the Q in the evaporator is going to be H1 minus H4 times M dot, but the M dot is the same in both of these cases, so we can cancel it out. And then the heat transfer, or the net power, happens across this compressor, which is H1 minus H2. Now, we might want to compare that to what's the maximum possible coefficient of performance we can get. And in that case, we put the cold temperature on top, because remember, the energy benefit is about removing stuff from the cold side, divided by the net work, right, which is the net heat. And if it's an ideal process, we can replace Q dot in minus Q dot out with Q hot minus Q cold, right? So then we can turn that into T hot minus T cold if the process is ideal. So here for the ideal, or the Carnot coefficient of performance, we take T cold divided by T hot minus T cold. But we have to remember that because in the numerator here, this temperature stands alone, it's not a delta T, that T cold has to be in Kelvin or in Rankine, not Celsius or Fahrenheit. So now, here, it's 2 for the price of 1 today. We're going to talk about vapor compression heat pumps. They're the same thing, right? The only difference is the energy benefit. Now, if we're drawing our little stick figure, the energy benefit is in heating up the hot side. So where we want to concern ourselves, the energy benefit, is this heat that's rejected from the condenser into the hot reservoir, right? So if you're using a heat pump to heat up your house in the wintertime, then this is the heat transfer that's the energy benefit, right? So it's going to be the exact same analysis on the compressor, the condenser, the valve, and the evaporator. You'll get the exact same answers, but now your energy benefit is the heat transfer on the hot side, which is our condenser. If you don't remember which one is the hot side and which one is the cold side, this is a great reason to draw out that TS diagram, right? Because T is on the vertical axis there. So the hot temperature is the high heat transfer process, and the cold temperature is the low heat transfer process. Here, right, we got this coefficient of performance, which is still energy benefit over energy cost. But now we are going to denote this by the Greek letter, what is this, gamma, right? Pretty sure. I don't know. I never remember. It's the squiggly one, right? This is the desired energy benefit divided by the energy cost. But now the energy benefit is the heat transfer rate on the hot side, and the energy cost is still the net power, but the net power is only the compressor power, because all the valve does is drop the pressure. There's no power associated with the valve. So here, from the expressions on the last page, which we get from the first law, it's going to be m dot times delta H, right? We can see that the coefficient of performance for this heat pump is going to be H3 minus H2 divided by H1 minus H2. We can take the absolute value here, but in this case, it's going to be heat out is negative divided by work in is negative. So both of these terms will be negative. You'll get a positive number anyway. We can compare this to the Carnot coefficient of performance. In this case, we put T hot on the top because in this heat pump, it's the heat transfer on the hot side. That's the energy benefit. And then we divide by T hot minus T cold. Again, you want to make sure you're using Kelvin or Rankine in the numerator there. Right? So basically, for heat pumps and refrigerators, they're the same cycle. You just got to know which heat transfer is the energy benefit. But now we get to this point that we see with all of these cycles. It's great that we got symbolic solutions, right? If you do that on a test, in short order, you're going to be able to demonstrate that you understand how to use the first law and how to simplify the first law by using a bunch of assumptions. But you're going to get to this point, right, where I think this is the third question on our list of 3, right? So the first question is, how do we characterize the cycle, right? What's the energy benefit? What's the energy cost? The second question is going to be, are we going to model the processes as open systems or closed systems, right? And then the third question is going to be, how are we going to fix the states? What's the fluid? So here the fluid, remember, we're moving back and forth across a vapor dome. So we're going to fix states in a way that's kind of like how we fix states for water. But if we're looking in the textbook, we got to look on different, in a different appendix, right? So the fluid here is a refrigerant, but the refrigerant is kind of like water in that we're going to be going back and forth across a vapor dome. So how do we find delta H for refrigerants? So we can use tables, right? So the tables, they're in the back of the textbook. If you do this, it's going to be just like looking up values for water. It's just you're in a different set of tables for subcooled liquids and two-phase mixtures and superheated vapors, right? We're going to learn today about how to fix states with a pH diagram. That's pressure versus enthalpy, right? So if you were doing an FE exam, this is the reference material they're going to give you. You can also find these on the DuPont website. For your ideal compressor, you're going to find the change in the specific enthalpy such that there's no change in specific entropy across the compressor. For the real compressor, you're going to then have to use the compressor efficiency. The good news is the valve, right? The valve doesn't have any kind of efficiency, right? And once you know the inlet state of the valve, even though the pressure is going to be different, the enthalpy is going to stay the same, right? So across the valve, delta H is equal to 0, or H in is equal to H out, right? So I guess that, most of this is hopefully not new. I guess the valve is somewhat new, but pretty easy when we think about delta H. As long as you remember that it's isenthalpic, delta H is equal to 0. The part here that's not new is this pH diagram. So we're going to spend the rest of the class today kind of going over this pH diagram, because the first time you look at it, it's maybe a little bit intimidating. It's got lines all over the place, which is actually helpful, but the first time you look at it is maybe a little bit frightening, right? So this is this pH diagram, sometimes called SUVA diagrams, right? I call it a pH diagram because it's pressure over here on the vertical axis versus enthalpy here on the horizontal axis, right? Now, when you look at this, you might be a little bit intimidated because there's so many lines, right? And if you take Thermo 2, you'll get another graph called a psychrometric chart, which you use when you're trying to figure out, when we relax the assumption. Because right now we're thinking about air just as air, but air has water in it, right? That's why you get dew in the morning. Psychrometrics allows you to sort of think about water in the air, but we don't have to worry about that in this class. But it's another chart like this that's super scary the first time you look at it, right? But when you look at this graph, the thing to remember is that it's a scaled version of a vapor dome, right? And it's got all these different lines on it because it's trying to give us just as much information as we would have in the textbook, right? So these pH diagrams are, they're vapor domes, right? Now, I apologize, the quality of this one isn't great. If I give you one of these on the exam to solve, which I've certainly done in the past, and I give you one of these charts, I'll ask you to solve this graphically on the chart, but I'll give you a higher quality version of the graph than is here, right? So here you can see, I guess it depends maybe how good your screen is, but the resolution here is not great. So there are better versions of this chart. They're just not in my presentation here. Right, so here's a little bit about these pH diagrams. It's pressure versus specific enthalpy, although they drop the word specific. They drop the word specific everywhere on this graph, but they're always, all the properties here are intensive versions of the properties, right? The cool thing is, this is like all the information in all of those charts, but it's graphical, right? So remember, we've been talking about, you can fix a state by having two independent intensive properties, right? So if we think about this on this pH diagram, if you have two independent intensive properties, you should be able to draw two lines, and those two lines should intersect somewhere, and where they intersect, that's your state point, right? So this is kind of cool. I think it's neat that we can solve these problems graphically, although, it's nice because we don't have to interpolate, so maybe it's a little faster, but we do sacrifice some accuracy because now we're sort of reading something graphically, right? So there's more uncertainty introduced into the process. So like I said, all of the different properties here drop the specific label. So if it's talking about enthalpy, it means specific enthalpy. And if it's talking about entropy, it means specific entropy. And if it's talking about volume, right, you get the picture, right? So pressure is just pressure, right? But it's important to remember this is absolute pressure on the graph. It should say specific enthalpy. Temperature and quality are always intensive. And then it says entropy and volume, but it should be specific entropy and specific volume. So how do I read this graph? It's a pH graph, right? So on the vertical axis, we have pressure. Notice that this is not a linear graph, right? This is a log chart, right? So if you're trying to look where these lines are, don't just assume that it's linear in between, right? But finding pressure is not that bad. They're just horizontal lines. If I want specific enthalpy, right? Again, this is a vertical line because this is my my x-axis, right? So if I'm looking for a line that's constant specific entropy, it will be a vertical line. So as I go through my valve, which is isenthalpic, right? It's going to be a vertical line on this graph because H does not change through the valve. Here, if I have temperature being constant, this is a little trickier, right? But here, you got to be careful. At least for me, it's sometimes a little difficult to tell the difference between 10 degrees and minus 10 degrees. So you got to be a little bit careful. You see, here's the zero line. It goes down. And then remember, temperature and pressure are dependent in the vapor dome. So it's a horizontal line here, and then it dives down. So I've kind of highlighted a couple of these lines here at minus 40, 20. This one looks like it's 100 degrees. And then I'm not sure, the temperature here is 200 degrees. Quality is only marked inside the vapor dome because quality only makes sense to talk about in the vapor dome. Here, if you look, this is 0.2, that's 20% quality, 30%, 40%, 50%, right? So these are on the, under the vapor dome. Saturated liquid over here on the left-hand side of the vapor dome. We crest the apex here past the critical point. Then we get saturated vapor on this side of the vapor dome. I find the specific entropy lines to be the most difficult ones to, kind of figure out on this graph. These are constant lines here, but they start off being pretty vertical, and then they kind of slant down as we move across the chart here. So these are the constant specific entropy lines. You can read the numbers down here. Although, again, I apologize that the quality of the print here isn't the best. Then we have specific volume. Specific volume is only graphically shown outside of the vapor dome. And it looks like this. It's kind of like, I don't know, I think about these as little like hairs that are on top of the vapor dome, right? These ones are standing straight up and they start to tilt a little bit more. And then they're just going sideways over here. So if we're looking for the numbers here for specific volumes, here's the numbers over here. right? And then, they start to draw them outside of the I guess, more dense lines. So those are all the different types of lines that we can have, right? So how do we fix a state using this graph, right? Because I'm telling you, you can use this instead of the textbook, right? So we still need two independent intensive properties. Each line, we can get a constant property on each line. And then we look for, once we know two independent properties, we look for where those two lines intersect, right? And once those two lines intersect, then I can look to see what's going on with all the other lines to get some kind of a graphical estimation for what the rest of my properties are, right? So here, it'd be good if you can print something out and maybe you're measuring things to get some idea if you're not exactly on top of a line, right? So we'll try an example here. So here's a pretty quick example. We're going to look at this heat transfer process where we have heat transfer coming into this evaporator, right? We got R134A that's flowing through the cold side of our evaporator, and we're adding heat. We know that state 1, the fluid is at a pressure of 5 bar and the quality is 0.2. And at state 2, the pressure is still 5 bar, so this is a constant pressure heat addition, but the temperature goes to 20 degrees. So we'll fix these two states and we'll find the heat transfer per unit mass flowing through our heat exchanger here. So we're looking to find little q dot. So I'm going to define my control volume. That's this. This is the cold side of our heat exchanger. I'll do conservation of mass, right? So I'm going to say this is at steady state, one inlet, one outlet. There's only one mass flow in my problem. The mass flow rate is the same at state 1 and state 2. I'm going to do the first law. Said we're going to be at steady state. We've already said that. We've already said that there's one inlet and one outlet. I'll neglect kinetic and potential energy changes. I'm going to say that this is a passive process. It's a heat transfer process. No friction losses inside this process, right? That's why it's constant pressure. And there's no heat losses kind of except for the heat that's being transferred. So basically all the heat that's going in goes into the fluid, right? So the increase in enthalpy we'll see in the cold side of the heat exchanger is all the heat that gets added, right? So when we do this first law, we get an expression that we're hopefully not that's hopefully not unexpected, is that Q dot is going to be M dot multiplied by H out minus H in, but we don't want big Q dot, we want little q dot, so we divide both sides by M dot, and we get that it's equal to H out minus H in, or in our case, H2 minus H1. So I don't know Q dot divided by M dot, I don't know H out, and I don't know H in, right? So this is what happens all the time in thermo. I can't solve the problem, but if I could fix the states, then I'd only have one equation with one unknown. So how do I fix the states? I'm going to use this chart. So first, I have state 1, which is 5 bar and 0.5 megapascals. Same thing, right? It's the same pressure, and the quality is 0.2. And state 2 is also at 5 bar, and the temperature is going to be at 20 degrees. So I got to fix these two states, right? So let's find state 1 first, right? Remember, this is my vapor dome. I'm looking for a pressure of 0.5 megapascals. So this pressure is in megapascals, right? So if this was in bar, I would have had to convert it, right? So here's 0.1, 0.2, 0.4, there's 0.5. So because this is a log scale, it's not exactly halfway in between. I got to look for the next dotted line. Oh, that's 0.05, right? So here, sorry, this is 0.4, there's 0.6, right? And the line in between there is over here, right? So this is 0.5 megapascals, right? It's always good to, right? You got to measure twice and cut once, right? So I found my mistake there. My quality here is at 0.2, right? So now quality only makes sense under the vapor dome. Here's saturated liquid. There's 0.1 and here's 0.2, right? So this is my second property there. So where these two lines meet, I'm going to draw this purple dot, and then I'm going to draw a vertical line down, and I want to read the enthalpy, right? So now this, if I had a ruler, maybe I would measure how many millimeters are between 250 and 300, and then I'd see how far along, I could scale it up. I'm going to say that this was 260 kilojoules per kilogram, right? Now, let's say that I've never done this before, right? Or let's say you're skeptical of what I'm telling you, because we should always be a little bit skeptical of what people tell us, right? Especially in an election year, right? So how do we figure out if this number's right? Well, we know the textbook, right? So I looked up this same thing in the textbook, and if you believe me that I know how to look up numbers in the textbook, then I get a problem, right? Because here on this graph, H1 is 260 kilojoules per kilogram. But from the textbook, it's like 108.8 kilojoules per kilogram. So, I'm an engineer, I'm not a mathematician, but I do know that 260 is not equal to 108.8. So what does this mean, right? Did I just terribly reread this? Did I get the wrong chart, right? Why is this number different? So the tricky thing with enthalpy is that just because you're measuring enthalpy doesn't mean you have the same 0 point, right? This is true in temperature too, right? Remember, we have degrees Celsius and degree Kelvin, and the difference between the tick marks on the thermometer, they're the same distance apart, but it's a different zero. It's also true with pressure, and maybe that's a better example because we have the same names for pressure. It's still in megapascals or bar, right? But absolute pressure takes 0 as the vacuum pressure, and gauge pressure takes 0 just as the local atmospheric pressure. So that's what's happening on this chart, is that the chart has a different 0 point than the textbook does, right? So what that means is that you can't do a problem half in the textbook and half on the chart. You got to pick one and go with it, right? So you can't do both, right? Even though they have the same units, the same name of the units, they have different zeros, right? So it's like absolute pressure and gauge pressure, right? The values are offset. So that's okay, because the first law only ever asks us for delta H, so we should get the same delta, just like you'll get the same delta T in Kelvin and in Celsius. This will work, right? So the textbook values are always just about 150 kilojoules per kilogram higher than the numbers that you'll find on these kind of charts from the FE handbook, right? So here, graphically, our difference was just over 150 kilojoules per kilogram. So my graphical guess wasn't terrible here, right? But you'll notice there definitely is error by doing this graphically. So now we fix state 1. Let's fix state 2, right? So here, now I have a pressure of 0.5 bar. It's still the same line, right? But now my temperature is 20 degrees. Now, like I said, it's sometimes tricky for me to see which one is negative 20 and which one's positive 20. So the numbers are going up here. So I look for 0 and then I go 10, 20, right? So it's going to be this line. You'll notice as this line comes down, it doesn't intersect my 0.5 megapascal line in the subcooled liquid region. So that means we zip right across here to saturated vapor and we come down over here, right? So now my green line is this 20 degree line, and where these two lines meet is over here in the superheated vapor region. So what I want is H2. So I'll drop a vertical line down, and now I'll try to estimate what this specific enthalpy is over here, right? So here I estimated that the specific enthalpy was 412 kilojoules per kilogram. Maybe you would have said 410, maybe you would have said 415 or 420. That's fine, right? If you get a problem like this on an exam, I'm going to be grading your process and not necessarily your graphical estimation skills, right? The textbook will tell you here that H2 is 260.4 kilojoules per kilogram. So again, it's offset. And if my graphical estimation skills were perfect, it would be offset by the same amount, so that delta H from the textbook should be the same as delta H from the graph, right? So we'll check that out here. I'm going to find the answer for Q dot over M dot using both the graph and the textbook, right? So both ways, I know H out and I know H in. So let's find little Q dot, or Q dot over M dot, right? If I use the numbers from the FE handbook, right, or from this graph, then little Q dot is 152 kilojoules per kilogram. And if I use the textbook, right, then again, it's about 152 kilojoules per kilogram. So here again, my graphical estimation was reasonably good, right? Now, I would expect actually to not be this good, right? This is, 0.4 on 150. I wouldn't expect to be that accurate when I'm reading stuff graphically, right? So it'd be fine if you did this and you were a little bit less accurate than that. So that concludes the lecture for today. Next class, we'll do an example of a heat pump cycle, I believe, and we'll use the graph to sort of figure out how to fix all the states, right? So that if you do see that on an exam, you're ready to do it. But if not, then you're certainly welcome to use the textbook if it doesn't specify what to do. So if you're doing homework problems, you're certainly welcome to use the textbook to fix these states. And then you'll use the same strategies that we used essentially when we went through the Rankine cycle. So that's all I have for you today. Do you have any questions? All right. Well, thanks very much.